Hello, everyone. Now this presentation is about generative AI, and Yağmur Seda will class this presentation. Her mentor is Ozan Evkaya, but he's not present here. Therefore, I will introduce Yağmur for his sake. So Yağmur is a last year physics student in Boğaziçi University. And she will talk about generative AI, text-to-image, and that's things. Okay, now.
Hello, everyone. I will introduce today generative AI that can create new content like text, images, or music by learning from data. We will start with an overview of foundational models like recurrent neural networks, which handle sequences and time-based data. Then we will move to the powerful transformer models. Finally, we will touch on diffusion models. To understand generative AI, let's go hierarchical and start with artificial intelligence, which is a branch of computer science, deals with creation of intelligent systems, which think and act like human. In this discipline, we have machine learning. Machine learning is a program that trains a model, and this trained model can make useful predictions on previously unseen data. Two of the most common classes of machine learning models are unsupervised and supervised models. In supervised learning, model learns from past examples to predict future values, also uses labeled data where inputs are paired with known outputs. The model makes predictions and compares it to the training data. If the predicted and actual values are different, this is called an error. Model tries to reduce this error until the predicted and actual values are close together. This is a classical optimization problem. However, unsupervised learning deals with unlabeled data. Model identifies patterns or clusters in the data without predefined outputs. This allows the model to discover underlying structures independently. Deep learning is a type of machine learning. It uses artificial neural networks. Artificial neural networks are made up of many interconnected nodes or neurons. They can learn to perform tasks and make predictions. Here is generative AI. It is a subset of deep learning. Generative models learn the joint probability distribution or the probability of X and Y and predicts the conditional probability, so it can generate new content. Here, let's look at the generative AI types based on the input data. A generative language model takes text as input and can output more text, image, audio, or even decisions. A generative image model takes an image as input and can output text, another image, or video. Here is how generative AI works in the simplest term. The input data, such as text, is first converted into a vector representation. This vector representation captures key features. Neural network processes this vector and generates a new representation as output. This output vector converted back into the desired format, such as text. These are the main generative AI models. We will focus on transformers and diffusion models today. But before starting with transformers, we need to understand what sequence-to-sequence modeling is. Sec-to-sec models transform one sequence of data into another. Think of it as teaching a machine to understand and generate human-like text. The most common structure for implementing sec-to-sec model is encoder-decoder model. The network takes an input sequence and generates a contextualized representation, often referred as context. This representation is delivered to a decoder, which generates a task-specific output sequence. Here, one of the fundamental architecture used in sec-to-sec modeling, which is RNN. RNN is a type of neural network, process sequential data. At each step, RNN takes in two inputs, the current input data and the history, which is the output from previous step. An RNN typically consists of three key components: input layer, hidden layer, and output layer. Input layer receives initial data element, which represented as a vector. Hidden layers are networks, process the current input, and combines it with previous hidden state. This maintains the understanding of context. But how RNN works? It has mainly four steps. Faisal's voice is on. Okay. How RNN works? It has mainly four steps: forward pass, loss calculation, backward pass, and updating parameters. Let's look closer to the RNN architecture and workflow. At each time step t, RNN process an input xt, updates its hidden state at, and generates an output yt. All of them are expressed here. Hidden state at is updated at each time step using the current input xt and previous hidden state at-1. WAA, the weight matrix for hidden state. WAX is weight matrix for input. BA is the bias term for hidden layer. G is the activation function, such as sigmoid is shown here. Activation function adds nonlinearity to the network, allows it to learn complex patterns. Also, sigmoid function squares the input into range between 0 and 1. It is good for probabilistic interpretations. For calculating output yt, each time step, model use hidden state at, weights, biases in the nonlinear function g. In case you haven't heard, weights and biases are fundamental to neural networks. Weights learn from the data during training, determine the strength and direction of the connection between neurons. Bias helps in shifting activation function to better fit in data. We saw calculating hidden state, which was the forward process. When it comes to training and RNN, we use a method called backpropagation through time. Aim is reducing the difference between actual and predicted outputs, y hat t and yt. A loss function quantifies this difference for each time step, and total loss is the sum of the losses across all time steps. Backpropagation uses the chain rule to calculate the gradients. Gradients are the partial derivatives of the weights and partial derivatives of the loss function with respect to weights and biases. In each epoch, the model learns and updates weights and biases to minimize loss as it moves downward toward the error slope. Here we come to the bottlenecks of RNNs. Due to recursive nature of gradient calculations, two problems arise. Gradient can either shrink to near zero or grow exponentially. In vanishing problem, future gradients rarely affect at very first time step. As a result, RNN have trouble capturing long-term dependencies. Also, RNN process data sequentially. They couldn't use parallel computation capabilities of modern hardware, which make processes slow for long sequences. Also, RNN have computational inefficiency. They require the iteration to process the relationship between elements separated by distance d. Also, the relationship between elements ti and ti plus d becomes harder to capture as the distance d increases. So there is a solution, transformers. Transformers overcome the limitations of RNNs. Transformers consist of neural networks that learn the context of sequential data and generate new data. The transformer architecture has an encoder and a decoder. Unlike RNN, transformers don't have recurrency. They analyze relationships using a mathematical technique called attention. The encoder processes the input sequence and generates a rich representation through 6 layers. Each layer has 2 main components, a multi-head self-attention mechanism and a fully connected feed-forward network. Decoder has an additional attention layer, focuses on the encoder's output, which also use masking. Let's look at the encoder workflow a bit closer. Firstly, it converts input tokens into continuous vectors. Second step is to add the positional information of each token in the sequence. And when we do not process the data sequentially like RNNs, we need to add position. For this model, uses sine and cosine functions to create position vectors. Step 3 is to send vectors to the stack of encoder layers, in which there are a multi-headed attention mechanism and a fully connected network. I mentioned that unlike RNN, transformers use attention. This attention allows the model to relate each word in the input to every other word. It computes attention scores based on query, key, and value vectors. Query vector represents the token to be processed. Key represents each token in the input sequence. Value vectors update the query. And the attention mechanism compares the query with each key in the sequence to determine the relevance. The values are then weighted by these attention scores. Instead of calculating a single attention scores, multi-headed attention projects the queries, keys, and values into multiple subspaces, mean heads. Each head performs self-attention in parallel. This allows the model to focus on different parts of the input sequence and capture different features. Each encoder layer uses residual connections and layer normalization. This helps keep the input information and address the vanishing gradient problem. The outputs of all attention heads are combined and transformed to the final attention output. Then output passed through a 2-layer feed-forward network with relay activation function. Then the decoder. Decoder generates the next token by using the previously generated ones, takes input from the final encoder's layers output. It begins by applying input embeddings and positional encoding, like encoder. Then it applies multi-head self-attention to the input sequence, but make masking. It makes future tokens that only past and present tokens are considered when predicting the next token. Then it employs encoder-decoder attention, which computes attention scores between the decoder input and the encoder output. This step allows the decoder to focus on the most relevant parts of the input sequence for each token being generated. Following this, a 2-layer feed-forward network with relay activation is applied. To stabilize training and retain essential information from earlier layers, residual connections and layer normalizations are used. Finally, the decoder produces a probability distribution, which is used to predict the next token. This process repeats iteratively until the entire output sequence is generated. And this was how transformer works. Let's start image generation. While many approaches have been implemented for image generation, I will introduce diffusion models. Diffusion process defines a Markov chain, gradually adds random noise to the data, then a model is trained to reverse this process to construct desired data samples from the noise. Diffusion process is Markovian. This means each step depends only on the previous one. Also, this process is stochastic because it involves random noise at each step, uses continuous sample paths. Model makes smooth the transitions from noise to the data or vice versa, but not big jumps. Here, we have the original image xt equals 0. T determine at which step we are. We will define two functions. Q of xt given xt minus 1 correspond to the forward pass, and that adds noise to an image. The second function P is for the reverse process. It takes in an image xt and produces a sample xt minus 1 with less noise using the neural network. Now dive into the forward process. Here, this equation is the probability distribution of the diffusion models. The distribution is characterized by two parameters, mean and covariance. In variance, I is the identity matrix. BT is a parameter called variance schedule. It controls the amount of noise added at each step. All BTs are between 0 and 1. This ensures data is scaled so that the variance doesn't explode. We can evaluate xt at any arbitrary time step t. At is a hyperparameter here. Also, we have epsilon t minus 1, which represents the noise and is sampled from Gaussian distribution with mean vector 0 and covariance matrix identity, which indicates the noise is isotropic, meaning it has the same variance in all directions and noise components are independent. To express xt in terms of xt minus 2, we substitute the expression for xt minus 1. Then we can see how xt is progressively affected by noise from previous steps. If we extend this process recursively for n steps, we get this equation, where a hat t represents the cumulative product. After 1000 iterations of forward diffusion process, we reach a pure Gaussian noise. Reverse process starts with these noisy samples. xt is the pure Gaussian noise sample. Reverse process aims gradually transform it back into a meaningful data sample by removing the noise step by step. At each step, the reverse process aims the sample distribution from p theta, which is learned approximation of the true reverse process qt, which is learned approximation. The goal of training is to approximate this true reverse diffusion process Q with our model's learned diffusion probability, p theta. The expression for the true reverse mean mu t can be quite complex, but we can simplify this mean. If we can express x0 in terms of xt and the noise epsilon t using the forward diffusion properties, and substituting this expression for x0 into the formula for mu tilde, we reformulate the mean in terms of xt and epsilon. It was quite complex. Okay, the neural network is trained to predict mu theta that approximates the true mean mu tilde. The aim is to minimize the difference between these two means. The loss function can be written as L simple, where epsilon theta is the neural network's prediction of the noise. And iterative sampling starts from t equals capital T, moving backward to t equals 1. After t steps, finally, we obtain x0, which is the generated sample, which is close to the original data. In denoising diffusion process, we started with an original image, and generated a pure noise, learning how to reverse the process. Then we generate the original image from pure noise. Also, we gain ability to generate different images from noise. And that was the end of my speech. Thank you, everyone, for listening. Also, thanks to my mentor, Ozan Evkaya, for helping me in my learning process. Okay.